Welcome to LabMiss.com in our lab video series on Cisco SD-WAN. This is Metha, your instructor for this video series. For a complete list of our SD-WAN videos, you can visit our website under the routing switching section. There you can also sign up for our newsletters to receive the latest video updates. I first would like to welcome you guys to our yet another video series. I know we have a lot of our audience who have been following our lab video series, so if that's you, thank you very much and welcome back. But if this happens to be your first video series with us, welcome to Lab Minutes, and hopefully you have time to check out our other videos on our website. In our last few video series, we looked at Cisco software-defined network technologies. We began our journey in the data center, which was the Cisco ACI, and we had two video series on that, which was the basic and the advanced. In the last video series, we looked at the Cisco latest SDN technology in the campus access, which was the software-defined access with the DNA center. Now in this video series, we'll still continue our theme of the SDN, and this time it's going to be on the software-defined wide area network, or SD-WAN. SD-WAN has actually been around a few years now, and there are many products out there that are available. And Cisco, who is, as you know, a big player in the space, certainly did not miss out on this technology. So this video series will be about Cisco latest SD-WAN technology, and we will start in this video with some introduction and fundamental knowledge of the Cisco SD-WAN, and we will dive into our lab configuration for the remaining part of this video series. The goal of this video is to prep you with the basic knowledge in case you are new to the topic, but hopefully you already have some basic routing switching background and maybe even some experience with the traditional WAN technology, so you can appreciate what you are about to learn. With that said, let's get started. Now, just to give you some background on Cisco SD-WAN, prior to the Vipteller acquisition, Cisco SD-WAN at the time referred to the Intelligent WAN, or IWAN, which was developed by Cisco. IWAN was the combination of Cisco best-in-class technologies including DMVPN, performance routing or PFR, WAN acceleration or WAS, and Akamai Connect. One of the problems IWAN has was the lack of a true unified controller. The only controller concept IWAN had was the master controller as part of the PFR configuration that pushes out routing policies. While the majority of the configuration, the routers like DMVPN and tunnel interface and things like that still need to be done manually. Now, to address the configuration issue, Cisco came out with the IWAN app on the APIC EM server to help automate configuration, but even so, that didn't seem to work really well and certainly did not help accelerate the adoption rate of IWAN. The other problem with the IWAN was everything was on-prem without any cloud-based solution, which was what other vendors are already moving towards. In 2017, Cisco acquired a company called Vipteller, which at the time was considered a competitor to Cisco in the SD-WAN space. Vipteller was built on a controller-based architecture. As we will discuss in this video, controllers are the integral part of the entire solution, and the fact that these controllers can either be on-prem or in the cloud gives you even more flexibility. While there are probably still a lot of IWAN implementations at the time of this recording, which is in 2018, Cisco encouraged any new SD-WAN implementation to use Vipteller, and that might be something you guys already know and why you're watching this video series right now. So just to be absolutely clear before we proceed further in this video series does not cover Cisco IWAN, but we will cover the Cisco Vipteller SD-WAN. So if you hear me refer to Cisco SD-WAN, that means I'm talking about the Vipteller SD-WAN. So enough with the background, we are now going to start by looking at the different components and terminology in Cisco SD-WAN solution. First, we mentioned that Cisco SD-WAN operate on controller-based architecture, so controllers are the key components in the solution. There are three types of controllers in Cisco SD-WAN solution, as you can see in this diagram right here. You got vManage, vBond, and vSmart, and these terms are inherited from Vipteller. So this controller works together to make SD-WAN functions. They can be either in the cloud, maintained by Cisco, or if you prefer for security reason, it can also be on-prem in a form of VM, right? So cloud or on-prem controllers. The minimum requirements is to have one of each type of controllers, but multiple controllers of the same type in a form of clusters are possible and actually recommended for redundancy if you run these in production. And don't be intimidated the fact that we have 3 different types of controller right here. I must admit that when I started looking to the Viptela SD-WAN, and certainly wasn't quite sure what each of these controllers does. So I think it makes sense for us to actually go through that right now and help you guys understand the function of these controllers. All right, we're going to start at the vManaged NMS or Network Management Server. So vManaged provides the management front-end GUI to the system, and this includes certificates management, device registration, configuration deployment, and system monitoring. So vManaged is actually the key server right here where you do and perform most, if not all, of your configuration. Everything that you configure on a Cisco SD-WAN will most likely be done on vManaged. So this is going to be the controller that we will be spending most of our time on. All the WAN devices will always maintain management connection to vManaged, as being depicted right here in the gray dotted line. So down below we have some routers that have to continuously maintain management connection to vManaged, which makes sense. Next over here we have a vSmart controller. So vSmart is considered the routing core or brain of Cisco SD-WAN. It primarily maintains global overlay routing table, and this is done by learning and advertising routes to and from the WAN edge devices via a protocol called OMP. Okay, maybe I should grab a pen real quick and draw as I go. So we talked about vManaged. Right, next we have the vSmart, and vSmart controls the routing and oversees the overlay routing, and it maintains the OMP control connection to each of the WAN edge routers. Even though OMP is Viptela proprietary protocol somewhat, it is very similar to BGP, actually iBGP to be exact, with a route reflector. With the vSmart being the route reflector here, as you can see, it's a central connection of the vEdge, or the WAN edge now it's called. This means that each WAN edge device will maintain control peering connection to the vSmart only and not to each other. And that's exactly how the route reflector and route reflector client works. All routing policies, route manipulations, and filterings are performed on the vSmart controllers. And then the resulted route gets reflected on the WAN edge. Right, so all the policies happens right here. The route comes in from the WAN edge. vSmart perform whatever the routing policies you have configured on that, and then re-advertise it back out, right? And that could be manipulating the route attributes or perform route filtering, for example. In addition to controlling the routing, vSmart also assists with bringing up the data IPsec connection by distributing VPN credential between the WAN edge and also handle all of the ongoing VPN key management. Right. This is what's awesome about the solution, is that you don't have to manually manage all the IPsec key or credential, and the authentication between the WAN edge to bring up the IPsec tunnels is automatically taken care of for you. As you'll see later, there's actually nothing that we need to do for that to happen. So that's our vSmart. Next we have our vBON server, or vBON orchestrator. vBON is where everything comes together. And what that means is the vBON man's responsibility is to onboard devices into the SD-WAN system, and this includes authenticating all of the devices. And in the case of the WAN edge, it also helped the WAN edge right here find both vManaged and vSmart, so they can build management and control connections to them. vBON is the first entity that any devices will talk to, so it needs to have usually a publicly reachable address, especially if one of your transport is the internet. Also, if the devices are behind NAT, right, so maybe your device sitting behind some kind of firewall, so that's the NAT right here, the vBON also help those devices facilitate NAT transversal as well. The next component we're going to look at is the WAN edge, or the WAN edge router. WAN edge, previously known as Viptela vEdge. That was a general term that used to refer to the router, but now when you said vEdge, it's actually referred to the Viptela either hardware or vEdge Cloud, which is the virtual version of that product, right? Because Cisco side of the house used the IOS XE routers. Obviously, the WAN edge main function is to route data traffic and also perform either data plane function like QoS, ACL, or zone-based firewall. Each WAN edge has management connection to vManaged, as shown right here in the diagram, as well as the control OMP connection to vSmart for routing purposes. And then lastly, the data connection amongst themselves. Right there, there, and there. So like I mentioned, WAN edge comes in different form factors, inheriting from the viptellers or the physical vEdge routers. Right, those are the hardware platform. And then you have the virtual vEdge cloud, which is the VM version. Or you can use the Cisco supported ISR ASR routers running the iOS XE. Right, so those are the 3 WAN edge device choices that you will have. The next component that we have here is the ZTP or PNP. ZTP is short for Zero Touch Provisioning, and the PNP is obviously plug and play. So the two terminologies came from the ZTP is the vipteller, I guess legacy terminology, and the PNP is more like what Cisco is using right now. But the two terms are still valid. When the WAN edge comes up, it is programmed to connect to a predefined URL of the Zero Touch Provisioning servers in the case of the vEdge, because the vEdge again came from the vipteller, so it's still programmed to look for ZTP server, while the Cisco iOS XE device will be programmed to look for the Cisco PNP Connect. And you'll see all that later on when we get to those videos as well. So what ZTP and PNP server does is redirecting the device to the organization VBON. So the WAN edge makes the contact. This guy's basically redirect the WAN edge to talk to the VBON to perform the authentication. If the device has the configuration template already applied, and configuration is actually done on the vManage. Remember when router talks to, or the WAN edge talks to the VBON, VBON inform the WAN edge to make connection to the vManage. And if you already have like a device template already applied to a device that you added to vManage prior to that, then technically the device will be able to download the configuration and even upgrade its software version, right, and be up and running without any admin intervention. And that's the whole concept of Zero Touch Provisioning and plug and play. The ZTP server is usually hosted in the Cisco cloud, but you can also install your own enterprise ZTP server if you want, while the PNP Connect server is 100% hosted by Cisco. So that's ZTP and PNP. Next we have the transport network. SD-WAN would not make much sense without the network that transport your data packet between the WAN edge devices, and this is the transport network. We also sometimes call it as an underlay network. So the two terminologies is actually interchangeable, transport and underlay. The most common transport networks are, for example, MPLS, and let's just assume that most of you would have that, but also people are moving more and more towards using internet as a transport, so internet is also an option. And then there are option things like VPLS or the 3G, 4G wireless. You need to have at least one transport network, obviously, or better yet, multiple network for redundancy. Right? So most enterprise, if they want redundant, you would have two of these, whether it's of the same type, MPLS, internet, or the mixed type, like MPLS and internet. The transport network only provides connectivities between the WAN edge devices, so it only knows about the WAN IP address, right, which is the address right here, unless you do some kind of loopback on those WAN edge routers. But otherwise, the enterprise routes will be exchanged directly between the WAN edge over the overlay, which is our next terminology, the tunnel overlay right here. All right, so like most SDN solution, we have an overlay network. An overlay network runs on top of the transport or the underlay network to securely transport your data traffic. And for Cisco SD-WAN, this is in a form of IPsec. Right there, so those orange dotted line is the data IPsec tunnel. By default, the WAN edge devices built a full mesh, as you can see right here, overlay IPsec tunnel, and there's almost nothing that you need to do to bring up these tunnels, right? Because it's being negotiated and established dynamically or automatically for you by the system. All right, other than those components, there's a few terminologies that I want to get out of the way because you're going to see them keep coming back as we go through the configuration. The first terminology is system IP. Right there. So system IP is basically unique device identifier, similarly to a router ID, and it is very important because it is used at various places to make the Cisco SD-WAN works. And this could be part of your configuration as well. So every device must have a unique system IP. And some people also refer it as a loopback as well. In fact, I believe if you look at the show commands on the WAN edge later, it actually show up as a loopback. Next we have the site ID. So site ID marks a physical location that the device is located. So every device must be assigned a site ID. If the devices are located at the same site, usually for redundancy, right, when you have like a two or dual routers at the site, then they would have the same site ID. And that's just a numerical number. Then we have a domain ID. Domain ID is a group of vSmart and WAN edge devices that share the same routing information. So you need one domain ID per overlay. All right, and the last and actually quite important terminology is organization. That's how the system distinguishes between a different SD-WAN implementation. Organization defines a scope of your SD-WAN deployment and device ownerships. This is usually just a company name. As straightforward as you may think this is actually important. Devices do need to be configured with the same organization for them to communicate, and you will see this is one of the first things that we configure on the devices as well. If you have an organization configuration mismatched, then most likely the device will not talk to one another. There are definitely more terminology, but we will save those when we get to specific aspect of Cisco SD-WAN in a little bit. But these are the ones that certainly worth mentioning right now. That's because those are what drives the core function of the SD-WAN. Now that you know about the components in Cisco SD-WAN, let's see how they all come together into a deployment. So one of the things that I need to make you aware is every device needs to be authenticated before becoming part of the system, which makes complete sense for security, and a certificate authentication is exclusively used for that. This means the device needs to have a valid certificate one way or the other, so you can expect to see a lot of certificate generation and authentication happening in this bring up process. Devices also perform chassis number and certificate serial number validation. So not only that the device must have a valid certificate, but also the very specific ones that matches the device. Right? So you can't just grab a certificate from one device and then import to another, as it will fail the chassis and the serial number validation. This certainly minimizes the chance of having an authenticated or authorized device on your SD-WAN even further. All right, now let's talk about the Cisco SD-WAN bring up process, and this is the steps of a chain of events that usually happens when you first bring up an SD-WAN deployment, and we're going to step through that right now. Starting with number 1. By the way, just make note of all the devices up there: the vManage, the vBond, vSmart, ZTP, PNP, WAN Edge, and another WAN Edge. So everything starts off by you install a vManage and vBond. Right, then you add the vBond to vManage. The vManage issues a certificate to vBond so they can perform mutual certificate authentication and establish the management channel right here. Next, in step number 2, you will install your vSmart. Again, the former VM, add that to vManage, just like how we added the vBond. The vManage will do the same thing, issue a certificate to vSmart. But at the same time, it will also upload the vSmart information to vBond, because the vBond needs to know about vSmart, because vSmart is about to make a contact to vBond to perform authentication. Right, so vSmart perform mutual cert authentication with vBond, and vBond, who's already have information about vSmart, happily accept the vSmart certificate. See that's valid. At the end of the authentication process, vSmart will have a connection to vBond as well as vManage. Also not showing so much in this diagram, if you have multiple vSmart, they will learn about each other. Right, so if you have vSmart number 2, vSmart number 3 right here in the cluster, they will learn about each other from vBond over here, because the other two vSmart would have done the same thing to the vBond. Then the vBond will inform the vSmart about each other, and they will build a also full mesh control connection amongst themselves. At this point, the controller bring up process is complete. You have all three controllers up and running with connections established between them. And this is actually only relevant and important if you decide to go with the on-prem controller solution. If you use the Cisco Cloud hosted controllers, most, if not all of these should have been done for you by Cisco, and you actually would be starting your deployment at the step number 3. At step number 3, what you need to do is you need to make your vManage aware of all of the WAN edge devices that will be joining the network. And you do this by logging into the Cisco PnP Connect web portal, which will show you in a later video what that looks like, and then add the WAN edge devices to the portal. Okay, so you got your device list from the portal. Then you would have the vManage sync with their smart account and then download that device list right here. If you come from the traditional Viptela, you might be familiar with the whole serial number file that contains the device list. That's also signed by Viptela, right, so they cannot be forged. And then you need to import that to vManage manually. Just FYI, that file still exists or available, but you get that now from the Cisco PnP Connect page instead of the Viptela download page, which I'm not even sure if it's still accessible. Right, and you do that in the case that the vManage is on-prem and has no access to the internet. So you wouldn't be able to have your vManage connect to your smart account to download that list. So you have to do it manually out of band. Now the vManage has obtained the list of devices. It needs to upload that WAN edge information or list to vBond, right, who in turn pass on to vSmart. At this point, all of the controllers are fully aware of the WAN edge devices that are about to join the SD-WAN network. And any devices that are not on that list will not be able to join the SD-WAN, obviously, because the vBond who will get contacted initially will say, I don't know about you, WAN edge, you're not on my list, hence would not pass the authentication. All right, so getting that list is very important. Now we're at step number 4, assuming that the ZTP or PnP servers are in play here, the WAN edge will come up, obtain the DHCP IP, which is usually the case for the internet. Resolve the predefined URL. Remember, we talked about the predefined URL that the hardware WAN edge will come with, hard-coded. That points to either the ZTP in the case of vEdge and the PnP in case of the iOS XE device. All right, so we'll connect to that URL. And one step that I actually skip is the fact that at this point, the ZTP and the PnP server should already know about the WAN edge. For the ZTP, if you own the server, operate your own server, then you upload the list manually. But for the PnP, it would have been coming from the same PnP Connect device list that you add. That way, the server knows about the WAN edge and hence which organization it belongs, so it can correctly redirect to a proper vBond. And this is where the organization name also becomes very important, because you certainly don't want your device to be incorrectly redirected to somebody else's organization vBond. Right? You want that to talk to your own vBond. In the case of the WAN edge that is a hardware platform, they would already have the manufacturer cert installed and be able to authenticate with vBond. Because vBonds already have the device listed, the authentication would be successful. But for the vEdge Cloud, which is the VM that you basically install yourself, you wouldn't do the plug and play anyway or ZTP anyway. The device will need some startup config in order to get the certificate from vManage. When we go through the installation of the vEdge in the form of hardware versus the virtual machine, the step is slightly different, and again, you'll see that in a later video. But for now, assuming that the WAN edge, regardless of the form factor, has the valid, as long as they have valid cert, then they would be able to successfully authenticate with vBond, and the vBond will inform the WAN edge about how to get to the vManage and vSmart. And once the WAN edge device learns about vManage and vSmart, it will go ahead and reach out to authenticate with vSmart. Right here from WAN edge connects and authenticate to vSmart, and then establish the management channel to get things like configuration and software upgrade. Configuration and software. That's step number 5, establish the connection. At step number 6, WAN edge also reach out and authenticate with vSmart and establish the control channel, and this is for the OMP peering. When you see OMP, it means routing. Yep, and then have the OMP peering established. As the last step, step number 7, finally, WAN edge established the data IPsec tunnel with the other WAN edge, and at this point the traffic can start flowing through the IPsec overlay. Right, once the data start flowing, that completes the bring up process. And your SD-WAN deployment should at this point become operational. This is just a high level, and there are actually a lot more detail that has not been mentioned here, but this should give you at least a good idea to what has to happen in order to get the basic connectivity going between your WAN edge. Next, we are going to actually dive into more detail on each of the planes that makes up Cisco SD-WAN, and that includes the control, the data, and the management planes. And the first thing that we're going to start with is the control plane. It's actually very important for you guys to understand what's going on in each of the planes, and that's why I'm going to go into more detail right now. As I've already mentioned, control plane in the Cisco SD-WAN is implemented in a proprietary protocol called Overlay Management Protocol, or OMP. And the OMP session is usually protected in either DTLS or TLS with AES-256 encryption. And what OMP does is it manages the overlay communication by distributing routes and location mapping information. And I'll explain in a little bit what it means by location mapping. You can view this as a modified version of BGP due to their similarities. Right, the fact that it will be carrying a lot of attributes and it's going to be policy driven or base type of routing protocol as well. Just think of it like this. vSmart is your route reflector, which is the center of everything, right? Center of routing control points. And then your WAN edge is your route reflector client who has an OMP peering session with vSmart only in order to learn and advertise the routes, but they will never ever have a direct OMP peering with another WAN edge. So this will never happen, okay, in terms of OMP. You can see that all the lines points up to your vSmart. Because vSmart is so important and you can't afford to have it down, we can have multiple vSmarts in for the WAN edge to peer with. You can imagine if you have another vSmart right here, then you have another peering session going on for redundancy, as well as the load balancing in terms of having the session established, right? So for example, you can have 4 vSmart, but maybe each of the WAN edge only built 2 connection to the 2 closest vSmart. Just imagine when the deployment spans globally, right? So you might have a pair of vSmart at each of the geographical region. There are 3 types of routes that are exchanged over the OMP sessions, and they are, let's see if I have it listed here. Yep, OMP routes, the TLOC routes, and service route. But before I get into the detail of each of types of the routes, I need to introduce you to 2 more terminologies. All right, so again, there's going to be some new terminologies that we are going to run into throughout the Cisco SD-WAN just because some of these are inherited from Viptela. But that's okay, they're actually pretty easy to understand once you know what they are. The first terminology is color. Right here, transport color. So color, which is the name that is uniquely identify your transport. This could be called, for example, MPLS, internet, private with the number 1234, etc. They're actually predefined, and you see that when you configure the interface or tunnel interface, you have to assign color to it, and there's just a predefined drop-down that you select from. So our diagram here shows two transports, so you will be dealing with two colors. All right, that's just the color uniquely mark the transport, that's all it is. The second terminology, which can be somewhat confusing at first, is TLOC, which stands for transport location. TLOC is actually a combination of three things listed right here, and they are system IP, color, and encapsulation protocol. Right, and in terms of encapsulation, it's either IPsec or GRE. System IP terminology, or for dimension, is uniquely identify a WAN edge device, color we just talked about, and then encapsulation. With these three components together, TLOC basically uniquely identify a transport connection on a particular WAN edge. So the system IP tells which WAN edge device it is, the color tells which transport connection it is, and then over that it can be either GRE or IPsec, right? So together it will mark, for example, that's one TLOC right there, and that's another TLOC. So in our diagram, each WAN edge device has two transports, so they each will have two TLOC, and I believe, if I'm not mistaken, you can have up to 8 per WAN edge. It means you can have up to 7 or 8 transport connection. You're probably going to be running out of the WAN interface first anyway. Now let's go back to the types of routes, the OMP, the TLOC, and the service route. The OMP route are routes that represents your network or subnets that you want to advertise into the overlay. So that's just your enterprise route basically. An OMP route is made up of, as I show right here, a network prefix, a TLOC, and some route attributes. So again, imagine this as being like a BGP route or something. The network prefix is obviously the destination of that route. The TLOC tells the receiving routers how to get to that prefix or destination. And I guess the TLOC is almost equivalent to the next hop IP in the BGP. It's just to carry a little bit more information than just a single IP. All right, and then the route attributes is also similar to the BGP attributes. And there are, for example, the preference, the origin, the tag, and they can be used to influence a routing decision when you do the routing policy configuration of vSmart. So that's the OMP route. Next we have the TLOC route. So why do we even need the TLOC route? The TLOC alone right here only tells a WAN edge where to route the packet to, but it doesn't actually tell it how. So what a TLOC route does is it maps the TLOC right here to the actual destination device WAN IP address along with some other reachability information. Okay, just the attributes. Now for a packet to be routed, it's almost like a WAN edge needs to do a recursive lookup. First, it needs to check the OMP route to get to the next hop TLOC, and then need to look up the TLOC route or a matching TLOC routes to get to the tunnel termination point so it can establish the IPsec tunnel, right? Because the goal is for a WAN edge to learn the routes, figure it out where the routes is coming from, and then establish the IPsec connection to that WAN edge destination. So that destination IP address has to be learned from somewhere. In this case, it's carried inside the TLOC route. So from there, the device will be able to know where the tunnel is terminated, not just which device, but also which transport, right? Because the TLOC contains the color. Then the WAN edge can build the IPsec tunnel to that TLOC specifically. Conversely, if the WAN edge has the OMP route with a TLOC that does not have corresponding TLOC route, then it would not be able to build the IPsec tunnel, hence being able to route to it. So you always do need to have a valid TLOC route before the tunnel can actually come up. And the last type of routes that we have here is service route. Cisco SD-WAN allows you to have network services like firewall, IPS, and load balancer located at different sites. These services can be advertised in the form of service routes. So basically it's just a way of a WAN edge to inform the other WAN edge that it has these services that can be utilized. Right, so the service route is used by the WAN edge to pass traffic through one or more network service. So for example, this WAN edge right here might have a firewall hanging off, and it can tell the rest of the network that this firewall is available for use. All right, so if it has more than one services, so it would be a firewall and then an IPS, right, or a load balancer, then it can potentially stitch the traffic together, and this process is known as service chaining. Right? And we'll have probably a video on that topic as well. But if you don't have any of that, then the chances are you're not going to be seeing the service route. All right, so all of that is for the control plane. Moving on to the next plane, which is data plane. We are going to start our discussion on the data plane by looking at the concept of VPN. You can see it's got the word VPN everywhere here. So VPN concept is inherited from, again, Viptela, but technically it is nothing but a VRF. Right, so, and hopefully you guys knows what the VRF is. The virtual routing and forwarding, which is just the logical separation of the routing table. So each VPN has its own routing table that are isolated, just like VRF, but unlike VRF, that can have any names. VPN can only be the number. So that's one of the key differences. By default, there are two reserved VPN number, which are 0 and 512. VPN 512, also known as Management VN, is pretty straightforward. It is dedicated for out-of-band management interface. So this is very similar to the Management VRF that you might see on the ISR ASR routers. The VPN 0, on the other hand, also known as the Transport VPN, it is a lot more significant and mainly used for two things. One, it is used for IPsec tunnel termination. The interfaces that connects to a transport circuit or transport network is mandated to be in VPN 0. Although you usually source the IPsec tunnel from the physical interface, you can also create a loopback if you want, and then source it from there instead. All right, but the loopback obviously has to also be in VPN 0. If you're familiar with the concept of front door VRF in either DMVPN or FlexVPN, where you dedicate an entire VRF just for the WAN facing interfaces that does nothing but terminating IPsec tunnel, the VPN 0 is pretty much exactly that. Except for the fact that usually when you deal with the front door VRF, you would have one VRF per interface, but in this case, VPN 0 is being used on all of the interfaces. Now, the second use of the VPN 0 is to build control and management channels to the controller, although it is optional, as you can also use Management VPN 512 for that. So if you have a controller right here, you can have, as we talked about earlier, right, the WAN edge builds the management control connections to the three types of controller. So it can either use the VPN 0 to do that, or you can also configure the 512 to do that as well. And as I mentioned, the system IP is part of VPN 0. Right, so system IP by default does not exist anywhere else but inside the VPN 0. VPN other than number 0 and 512 are considered a service facing. In other words, these are your local network you want to transport across the overlay and will be encapsulated inside the IPsec tunnel. Right, so you got the service VPN on the back side here. You can have as many service VPN as you like, right? So 1 through N. The traffic from each service VPN will be tagged with their corresponding VPN number, so they remain segregated when they're sent from one WAN edge to another inside the same IPsec tunnel. Right? So this is your IPsec tunnel, and then your encapsulated traffic will be tagged by the VPN, so that way, with that VPN tag, the destination WAN edge will know exactly which VPN to place the traffic into. All right, so having that tag works out pretty well, because instead of traditionally where you have to have multiple tunnel interfaces with the VRF assigned to each one of them, with that tag, you can carry the traffic from different VPN and VRF inside the same tunnel. So it definitely has a better efficiency doing it this way, right, while achieving the same result. And this is basically the segmentation capability of Cisco SD-WAN. Traffic goes into the WAN edge from one VPN, should be coming out and be dropped into the exact same VPN. Right, and the traffic by default does not cross between VPN. So on the vEdge devices, you see this shown as VPN, vEdge being the legacy Viptela hardware. And on the iOS XE router, this actually gets translated into a VRF. So for example, if you have a VPN number 2, then in the iOS XE, when you do show commands, it will come up as VRF number 2. All right. One thing that I have found pretty interesting when I start learning about Cisco SD-WAN is that for scalability, Cisco SD-WAN does not use IKE or IKE protocol. I think I stands for Internet Key Exchange, right? Whether it's version 1 or version 2, in order to establish the IPsec tunnel. So how exactly does the IPsec tunnel get negotiated and established? If you know IKE, you know that it is used to perform mutual authentication and key exchange between two IPsec peers. Well, since each of the WAN edge will already have a secure DTLS control connection to vSmart, which I'm not showing right here, so that could be your vSmart right there, right? So it has a control connection already to vSmart, authenticated, secure because it's DTLS or TLS encrypted. And that session or connection is where the OMP peering is running over. It's just basically use that same connection for key exchange with vSmart being the entity that facilitates the key distribution. Right? So it's just basically piggybacking that control connection, and KeySmart perform the key exchange for the WAN edge. In fact, the AES key that's used to build the IPsec session is tied to the OMP route advertisement. And that way, the authentication is implicitly assumed from the already established control connection. Right? So I find that's pretty neat. And just to be clear, this is only for the IPsec on the transport side. You can still use the IKE and IPsec combination on the server side if you have, for example, a VPN peer over here that you need to build a tunnel to the service VPN, right? And that's supported, just not on the transport facing. But all the details are hidden for you anyway because it's all being done automatically in the background. Okay, but that's just FYI. And the last thing I want to touch upon under the data plane perspective is the bidirectional forwarding detection, or BFD. For every IPsec tunnel, the WAN edge maintains BFD sessions in order to check if the TLOC is still reachable. Right? TLOC means a particular interface of the router, basically. And I say TLOC and not a router, because a TLOC can be down while the router remains up. There's no concept of idle timeout on the IPsec tunnel. As long as the BFD session between TLOCs are valid, the IPsec session will stay up. Right? So the BFD is running over that IPsec. If the BFD session times out, however, the router knows that the TLOC has become invalid, and that could be that the circuit has gone down or that entire router has gone down. So any routes associated to that TLOC needs to be removed from the routing table, and that's when the failover can take place. Right? So for example, this router might be advertising the exact same route out of both TLOCs, or for both TLOCs. Then if that TLOC goes away, the BFD sessions will go down, and this router right here can intelligently flip over and use this IPsec connection instead. BFD actually does more than just reachability check. It also measures path quality and maintain path matrix, and this includes delay jitter and loss, or packet loss, which can later on be used in traffic routing decision. And we will look at this in more detail when we get to the application-aware routing. So those are the key components and concept for the data plane. And the last but not least that we have is the management plane. One of the biggest benefit of Cisco SD-WAN is the centralized management. So vManage is used to perform all of the configuration, and it will push them out to both controllers, right? Not just the WAN edge, right? But obviously it's also pushed out to WAN edge. but vManager can be used to configure the controller as well, including itself. Command line is still available, and in fact, CLI mode is the default mode on all of the devices. This is because it usually needs to do some manual configuration initially on the device in order to establish connectivity to vManage, but once they are in communication, you can switch them over to what's called vManage mode, at which point you can no longer use CLI to configure the device, but only for the show commands to do the monitoring and troubleshooting. Right, so you got two modes, CLI mode, which is a default, and the vManage mode, which is, I guess, the preferred centralized configuration mode. There's a concept of template, right? This is to promote the configuration standard, modularity, and scalability. The vManage use something called configuration templates. Pretty much all of the supported features can be configured in feature templates. For instance, global config like location, SNMP, syslog, DNS server, OMP, or a more device-specific config like interfaces and VPN. All right, when you have all those features template created, you can select those templates and make a device template. So device template is nothing but a selection of feature templates that you can apply to the devices. Again, WAN edge and controller included. Feature templates can be shared by devices to ensure configuration consistency, right? That's the whole benefit of doing it this way with the template. For the most part, you use these configuration templates to bring up SD-WAN overlay with basic connectivity. And I say that because the second half of the configuration, which I would say the more important half, is the policy configuration that will dictate how your SD-WAN will actually behave beyond the basic connectivity. So the true power of the Cisco SD-WAN comes in with the policy configuration. Policy allows you to control how the traffic flows through the WAN edge and across the overlay. To be honest with you, everything that we have discussed up until this point, whether they are the system bring-up process or the template configuration to create the basic overlay connectivity, is pretty much almost the same in most SD-WAN deployment. What would make a deployment difference from one another is the policy configuration. So you can expect to spend a good amount of time on coming up with your own policy to get the traffic flow that you want. And there are 4 types of policies, and they are centralized control policy, right there, centralized data policy, localized control policy, and localized data policy. These policies get applied at different places, and some of which may even overlap in function somewhat. So let's go through them and see what they do. Centralized control policy is probably the easiest to remember. Centralized control policy controls how routes are learned and advertised. So learn and advertise to and from vSmart over the OMP session. I guess this is very similar to having like a route map that you can apply inbound or outbound of a route reflector. So you can filter or manipulate routes, right, with the policy. The policy is only applied to vSmart, and the WAN edge only gets to see the resulting routes after the policy has already processed the routes. So you use the centralized control policy to create different types of topology like hub and spoke, because by default it's a full mesh, or you can do also a partial mesh as well by configuring the policy, or you can influence routing by allowing, denying, and modifying routes attributes. All right, so pretty much a lot of things you can do in the route map on a traditional Cisco router, you can do on the centralized control policy. It's just that it's being done centrally as opposed to at the WAN edge devices. Next, we have the centralized data policy, which is the policy that affects the actual data packet directly. You will have an ability to match data packet by IP port protocols, right? Just basic field in the packet header, similarly to what you do in an access control list, or even by application if you want to do application-based matching and deep packet inspection, right? Then perform whatever actions on that packet. And this can be dropping packets, performing QoS, classification, marking, policing, change the next hop, or updating the T-log information on the packet. So we're not dealing with routes here again, we are dealing with the packet directly, so it's on the per packet basis. The policy can be applied on the WAN edge to the traffic that's coming from the transport or the service, right? Or you can do both as well. Because this is centralized configuration, the config is pushed from vSmart and stored on the WAN edge memory, and it doesn't really get into the device local configuration. So every time you see centralized, it means the config is not actually on the WAN edge. All right, then we have a localized control policy. All it does is filtering and manipulating OSPF and BGP routes coming from or going to the local service VPN. So if you happen to run OSPF or BGP, right, it's just a policy that allows you to do a route filtering and manipulation on those. And this is only on the service-facing VPN. So that one is also straightforward, localized control policy. And the last we have is the localized data policy. And this is similar to the centralized data policy. As you can see, the similarities in the names and where it actually takes effect. And they're similar in that it matches the packet and performs some sort of actions, with the difference being the policy for the localized data policy is actually pushed and become part of the WAN edge config, right? And this is applied also per interface. So if this guy has multiple interfaces, then the policy will be applied at those interfaces as opposed to either from transport, from service, and that's per VPN, right, for the centralized data policy. So that's the differences. For the most part, localized data policy is used to configure QoS and traffic mirroring. Even though it's not so obvious, but after you have actually gone through the configuration, you will see that each of these policies has its own purpose, and that kind of dictates how it should be used. And that's pretty much everything I would like to cover in our fundamental video. One thing that I purposely left out in our discussion here was the licensing, since the licensing could change over time. But all devices needs to be licensed, so definitely consult the Cisco ordering guide or your Cisco partner to get the latest information on that. Hopefully what we went through in this video got you started on the Cisco SD-WAN so you don't become completely lost for the rest of our video series. Just keep in mind that this video only gives you the overview of the Cisco SD-WAN. If you still have doubts in certain topics, don't worry, we will be covering them in more detail as we get into the configuration session of the lab. And trust me, we do have a lot to cover in this video series. Better yet, if you want to get a better understanding of the whole thing, you can rewatch the videos or definitely go to the Cisco online documentations and look into some of the topics that you have doubt on. What we are going to do in the next video is we are going to perform controller installation, so that will be our first configuration video. And that wraps up our video on SD-WAN Fundamental. You can visit our website to view an extensive list of our lab videos and sign up to get access to additional lab contents. Thank you for watching labminutes.com, and I'll see you guys in the next video.